On disk, we have hundreds to thousands of gigabytes of storage. So on disk, lots of data. When you look up in the SGA, SGA is going to be measured in either single-digit or double-digit gigabytes. So an SGA might be 1 gigabyte in size, 16 gigabytes in size. It's probably not 360 gigabytes in size. That's a lot of memory. So our data is measured in hundreds to thousands of gigabytes. And our memory is measured in tens of gigabytes. Solid-state disk drives will be measured in hundreds of gigabytes. Not thousands, but hundreds of gigabytes. So the solid-state disk drive will be smaller than our total database size typically, but much larger than our real SGA size, much larger than real memory. And this is how we'll use it. When you do a read for the first time after starting up the database, we're going to have to do a physical I/O against disk to copy the block from disk into memory. Eventually, my buffer cache will fill up, run out of space, because I have more data on disk than I have memory allocated to the system. And when that happens, Oracle would write the block out to disk to make room for new blocks. So we do lots of reading and writing and reading and writing over and over again. We'd like to avoid having to do this read over and over and over again. So with the flash cache, when we write those blocks out to disk, at the same time, we're going to write it out to the flash cache. So it will now be in both places. The next time we need that database block, we're not going to have to go to disk anymore. We're going to remember in the SGA that a copy of that block resides over here on the solid-state device. We're going to read it from there and move it back in the buffer cache. The fastest way to get your database block will be to find it in the cache. If it's not in the cache, the second fastest way is going to be getting it off the solid-state device. This will be 30 to 40 times faster than getting it off of disk itself, off of a physical magnetic storage device. So the flash cache works as an extension to your buffer cache. It's not going to be as fast as if the block was in the buffer cache, but it's going to be 30 to 40 times faster than if we had to get it off of disk. So the goal here is to keep as much data as possible, more, off of the disk in an area that we can access it very rapidly. And that's what the flash cache is about. And again, this is for Sun Solaris, Enterprise Linux. And if you've heard about Oracle Exadata, a hardware solution, this is not to be confused with the flash cache that's part of Exadata. This operates independently, separately from Exadata, and works at the server level, not down at the storage level. So this is something the Oracle server utilizes with the buffer cache on the database machine itself, not down at the storage array. Number 9. Some improvements to parallel query. I joined Oracle in 1993. Version 7 was going to production. In 1994, they released version 7.1.6. That was the first release of Oracle that had parallel query, that had parallel create index, that had parallel load. So that was the first parallel edition of Oracle. That was 1994. In 1994, if you looked at a big database server, it it would probably have around 64 to 128 megabytes, not gigabytes, of memory. It might have had 2 or 4 CPUs. That was a big server. A few CPUs, very little memory, and maybe a lot of disk. Our algorithms for parallel query were invented for a machine with very little memory and lots of disk. So they were very oriented towards disk operations. In the year 2010, it's changed a lot. Instead of 128 megabytes of memory, you have 256 gigabytes of memory. So we have a lot more memory on the machine now. But our algorithms never changed to take advantage of this. So in 11G Release 2, we made 3 major changes. The first one has to do with utilizing the CPUs correctly. We used to have 2 or 4 CPUs. Now we might have 64 or 128 cores, CPUs on our machines. We'd like to be able to take advantage of these in an efficient fashion, in an intelligent fashion. In the past, the DBA would have to look at the table and decide what the best degree of parallelism, how many threads should be processed simultaneously against a given table, just by looking at the table. So they would look at the table and say, that's really big. Make that table parallel 32. Use 32 threads of execution against it. Sometimes 32 was the right degree of parallelism for that table, for some queries. Sometimes 16 was the right degree of parallelism. Sometimes 1 was the right degree of parallelism, and maybe other times 128 was the right degree of parallelism. There was no single number that you could assign to a table that was right in all cases. So it was very hard for the DBA to tune. We had algorithms that tried to figure it out, but they were all based on the size of the table itself. In 11G Release 2, it's completely changed. What happens in this release is the SQL statement comes in, and the very first thing we do is generate a plan that does not involve parallel query at all. So we start with a regular query plan, no parallel. We estimate how long that query is going to take to execute without parallel. If that query is going to execute fast enough, the DBA tells us how fast enough is. We just execute it using parallel 1, a serial execution, no parallel at all. On the other hand, if it exceeds that threshold the DBA set up, we're going to generate a parallel plan. The degree of parallelism that we will use will be based on the query and the table, not just the table itself. So we'll look at the where clause that's being used. We'll look at the other tables it's joined to. We'll look at the entire query and say, this time, for this query, we should use parallel 16 for this table. Maybe in another query, we decide to use parallel 4 for that same table. It's going to depend query by query. So we come up with the degree of parallelism based on the query, not just the table. That's a major change. The second major change is parallel statement queuing. With parallel query in the past, if somebody submitted a query that we decided to do with parallel 32, we're going to run 32 things at once, we would start running that query. 32 things would happen. If 2 people ran that query, we would do 64 things at once. If 4 people ran that query, we would do 128 things at once.